homomorphism. If you are someone who have already did some Lie algebra or group theory, you might have heard this thing, homomorphism, but it's a more general definition. So let's say there is some map, again x to y, and it preserves, this map preserves certain algebraic structures, then it's called a homomorphism. Okay,
So এটা কি হোমিওমরফিজম থেকে আলাদা নাকি?
different. Homeomorphism is another thing. It's homomorphism, right? It's not homeomorphism. Homeomorphism is a completely different thing. So let's say how to say this, if you have two elements in your set x, let's say a and b, and you define some algebraic structure, let's say some product like this ab, it means something. What does it mean? We don't know. At this point it's abstract. So when you use this mapping over this product like this, let's say f of ab, on your set y, the product will be written like this. And a very simple example is the determinant of a matrix. If you call this small a some capital A and this small b some capital B, where A and B belongs to some n cross n matrix, invertible, let me write invertible, okay, then you can easily identify the homomorphism as the determinant of A times determinant of B. This is one very simple example of homomorphism. So if you have some algebraic structure, they can be product, they can be some sort of an addition, they can be many things, or commutation relationships, anti-commutation relationships. If under such mapping the structure it doesn't, if you see that the structure doesn't change, then it's called a homomorphism. And you may ask, okay, how is this structure related with this product? Okay, so let me give you a rationale over here, is that on your set x you define some sort of a product like this, right? Then if you want to uh, define some product that is similar to x, by similar I mean the same, then on your set y you have elements like this, right? F of a and f of b. Then how should you write it? F of a times f of b, right? This is something everyone understands, I think, at this point. So under this mapping, okay, under this mapping we can write this. This equation actually means that the algebraic structure is preserved. Yeah, that's about it. And how do you find these homomorphisms? Well, it from what I've seen in my group theory course, it's pretty easier to just guess sometimes, especially when you deal with matrices. But in later part of this course, we'll rather focus on how we can use these theorems to do some problems in physics and all that sort of stuff. So for now, just take this definition in, and maybe later we'll see how to find these stuffs and how to apply them in different scenarios. So is this homomorphism thing clear to everybody?
স্যার এখানে এই f of ab is equal to f of a f of b এই ক্যারেক্টারিস্টিক্সটা হোমোমরফিজম নাকি x আর y যেই ম্যাপটা আছে এদেরকে হোমোমরফিজম বলে?
The map is a homomorphic map. The map
আচ্ছা
F is a homomorphic map that is preserving the way you know, for example, in our example that we saw here, we defined some product AB, right? So if this F is a homomorphic map, it will preserve this the structure of this product. For example, this determinant thing. Okay.
ওকে
So if you are asking, okay, what are we calling this? I mean, who are we calling this homomorphic and stuff? It's the map, and the homomorphism is the preservation of this algebraic structure.
ওকে গট ইট
Okay. Okay. When you talk about homomorphism, you also talk about isomorphism. So if your homomorphism is a bijective one, then it's called an isomorphism. If a homomorphism is bijective, then it's called an isomorphism. Okay, that's the definition of an isomorphism. Yeah. And I think one example I can give right now, although I don't exactly remember it right now. If you are familiar with some groups or representations, then I think you have seen that the special orthogonal group SO3, you can write it as a double covering of some SU2, right? And they're isomorphic to each other. Okay, let's not talk about, I think a lot of you haven't done group theory, so let's not talk about group theory. Okay, this is just a definition, and later when we do some manifolds and all that stuff, we'll see these things will come again and again. So that's why I wanted to introduce these definitions today. And this is yeah, this is it for the definitions. So if you have any questions, you can ask. If not, I'll move on. Okay. The next thing we want to discuss is something pretty nice, and I think it's pretty new, unless you are already familiar with some advanced topological stuff. We want to discuss something called an equivalence relation and equivalence class. So what is the equivalence relation? An equivalence relation is say it's a relation that satisfies the following axioms or requirements, whatever you want to call them, that satisfies the following, and it is given by some equivalence symbol. If you are someone who has done LaTeX, then you write it as /equi, right? So the requirements are the following. Again, I'm stuck. The first one is that, let's say the element that we're considering, at this time we don't really bother with the sets, just some element A is equivalent to A, and this is called a reflective property. The second one is the symmetric one. Let's say we have two elements A and B, and we are saying that there is some sort of equivalence relation between them. If that's true, then it has to satisfy A equivalent to B and B equivalent to A. This is known as the symmetric property. And the third one is something we call a transitive property. And let's say instead of A, B, we have now A, B, and C. And we say A and B are equivalent, B and C are equivalent. So we write A equivalent to B, B equivalent to C. So if A equivalent to B and B equivalent to C, then A has some sort of equivalence relation with C. This is called a transitive property. This is the definition of a equivalence relation. And let me give you an example right now. Let's say we have two integers, m and n, okay? And we divide them by 2. What is the remainder? It's either 0 or 1 in both of these cases, right? So I think you guys seen this thing, right? M mod 2. It just this is a way of writing the remainder. Has everyone seen this?
Yes, sir.
Okay. It just means an m modulo 2, okay? So let's say if this is 1, and let's say n mod 2 is also 1, then we can say that there is equivalence between m and n. Why? Because if I consider the modulo by 2, then they're equivalent to each other. Okay.
So let's suppose m is 3 and n is 5.
Hmm.
Both 3 and 5 mod 2 is 1. So I can say 5 is equivalent to 3. Does that mean they have a common characteristics and they are odd number? Is this the equivalence?
The equivalence is coming from the fact that we are defining the relationship after modding by 2. So yeah, they're odd numbers, but I wouldn't like to say that being odd is the equivalence here. I would rather stick to the point that whenever I divide those numbers by 2, I have this reminder, which is 1.
Oh, got it.
I want to stick to that. That's more precise. Yes, it's true that they're odd and stuff, but I don't want to go there because
এই
when
ইয়েটার ডেফিনেশনটার মানে ইয়ে হচ্ছে যে এম আর এন ইকুইভ্যালেন্ট হবে যদি তাদের ডিফারেন্স দুই দ্বারা বিভাজ্য হয়।
কি বলছো বুঝি নাই।
মানে এম আর এন ইকুইভ্যালেন্ট হবে যদি তাদের ডিফারেন্স দুই দ্বারা বিভাজ্য হয়। মানে ইভেনের ক্ষেত্রেও যদি মানে 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 আরেকটা তো জিরো ধরতে হবে, মানে এম মড 2
দুইটা কেস আছে। আর 0 আর 1 কে আমি কখনো তো ইকুইভ্যালেন্ট বলতে পারবো না আন্ডার মড 2,
কারণ তাদের ডিফারেন্স দুই দ্বারা বিভাজ্য না। মানে চোর আর বিচোরের ডিফারেন্স তো বিচোর।
I don't know. আচ্ছা আমি ফিজিক্সের আচ্ছা না orbifold, I shouldn't say orbifold right now. Orbifold, yeah. আচ্ছা, don't worry about orbifolds right now. So I think what Nian was saying is something related with some math Olympiad problem, and I'm very bad at those things, so I'm not gonna say anything over that. So yeah, that's how I want to see it. Like আমি ডেফিনেশনের সাথে স্টিক করে যতটুকু মানে ইকুইভ্যালেন্স রিলেশনটা ডিফাইন করতে চাবো আর কি। That's how I want to see it. আমি এর থেকে বাইরে যাব না। I'm gonna be very strict. মানে I won't give much freedom to myself when I'm dealing with this sort of stuff. So this is a simple example. Okay, so we are done with the definition of this equivalence relation, and now we come to the definition of an equivalence class. In fact, there is another example in Nakahara. If you study the book, then if you have let's say some integer and you want to divide it by n, then there is the equivalence relation between the reminders that you will get. That means let's say you get divide something by number n, so what can the remainder be? The remainder is something from 0 to n minus 1, right? And that will be equal to some cyclic group Z of n. But I don't want to discuss that because I think some of you are not familiar with group theory, so I have to skip that, like how this equivalence is there and stuff like that. But we'll give some geometric pictures that how we use these relations and stuff very soon. So let's talk about the equivalence class right now. The definition of equivalence class goes as follows. Given a set X and an equivalence relation, which is given by this symbol, we can have a partition of X into mutually disjoint subsets that are called equivalent classes. And these classes or so to say the equivalent classes, let's denote them like this, is made of all the elements X in X, or X you can also write small x belongs to capital X, such that X has this equivalence relationship with A, some small a, and you finally write this as this is very buggy. Is this confusing? If you are confused, you should let me know. Like the class is made out of, there is some a, okay, some small a, and you have this set X, and let's say you divide this set into some distinct regions that don't intersect with each other, okay, and each of those regions can be considered as a equivalence class, and all the elements inside those classes are equivalent to each other. And the reason they have to be disjoint is coming from the fact that I'll just show you a sketch of the proof. So this is the reason they have to be disjoint. The rationale for the classes, by classes I mean the equivalent classes. Equivalent classes have to be disjoint. So let's say this is our set X, okay, and let's say we partition this guy into something like this. So this regions inside, they can be considered as your equivalence classes and stuff. Oops. Okay, and they're disjoint. Why? Let's consider a case where they're not disjoint. So again, this is your set X. Now let's consider two regions like this. This is one and this is another one, and they intersect, let's say. And you understand that let's say This is what this is written as some B, and this is written as some C. And there is a point, let's say this is point A. There is a point in C, this class, or so to say this subset. This is called C, and there is another point called B. Now, if you check with this definition of equivalence relation, you immediately realize the fact that this A is equivalent to C, right? Is that right?
Yeah, since A is in the equivalence class of C.
Yeah. At the same time, B is equivalent to A. So what does this tell me? This tells me that B and C are equivalent, right? So let's take another point in B. Let's say this is B prime, and B is also equivalent to B prime. And let's take another point in C, which is denoted by C prime, and C is equivalent to C prime, but B is equivalent to C, and at the same time B is equivalent to B prime, so you can write that B prime is equivalent to C, right? But C is again equivalent to C prime, so B prime is equivalent to C prime. So they cannot intersect each other, and if they do, they're the same thing. These two classes are the same thing. You can do this for all the points, right?
So they are equivalent with respect to A, B and C.
I'm just saying A is a reference point. Like
Oh, আচ্ছা।
আমি এটা করছি যাতে তোমরা একটু মানে কনফিউজ না খাও, ওকে?
Okay.
মানে যদি এরা দুজন ইন্টারসেক্ট করতো তাহলে এরা আসলে ডিস্টিংক্টই না। হ্যাঁ, কারণ হচ্ছে যে দেখো তুমি এইভাবে এই যে বি প্রাইম ধরে যে করলাম, ধরো there is some special point that lies in the intersection of these two subsets. Okay? I can hear my voice. Can anyone turn off the loudspeaker? It's very weird. Okay, thank you. So let's say there is some sort of special point. There is something special about the intersection, and let's call that special point A, that lives in between the equivalent classes B and C, which are some subsets of X. Now A is equivalent to, since A lies in B, A is equivalent to all the points inside B, and A also lies in C, so A is equivalent to all the points in C. So by the very definition of equivalence relation, we can say that all the points in B are equivalent to all the points in C. So they have to be the same class, right? This B and C, they have to be mutually disjoint, because if they are not disjoint, they have to be the same thing. In fact, you also have to show that, because you are dealing with sets, you also have to show that this B subset, B is a subset of C and C is a subset of B, and you can also do that using those definitions of this guy. So this is again an exercise. Again, I will include the answers in the lecture notes. So first thing you should do is that you try to come up with some logics. Don't worry if you cannot do it. I will just include them in the notes as well. So the exercise is that you show that these two equivalence classes, okay, show that either these two equivalence classes are disjoint, or they're the same thing, or if this is not, this is the null set, null, phaka, whatever you want to call it. If this is not the case, then they're equal, they're the same thing.
Sir, can you explain the equivalence class definition again?
Equivalence class definition. you have some set and some equivalence relation on that set. Okay, then what you can do, you can partition that set like this. These are small partitions, and all the points inside this, let's take this red region over here. All the points inside this red region are equivalent to each other, and this itself is equivalence class.
Oh, got it.
Okay, so yeah, this is a new thing, I think, for most of you. So this is a pretty interesting thing, and I'll just give some one or two more definitions, and then I'll show you something interesting. Any
The
questions so far?
The exercise you gave says that if the class are
If
destroyed,
they're,
they
yeah,
are empty. If they are not, they are the same class.
yeah,
Okay.
okay. I'll include the answers in the lecture notes, so don't worry about it. But yeah, you should try. You should at least try. Okay, so let's talk about some other things right now. So we discussed this equivalence stuffs and all that stuff. And when we identified equivalence classes within a set, we had some regions, right? Like this. Okay, someone is trying to tell me something. Why don't you open your mic? Basically, most of advanced mathematics. Okay, good. Oh, okay. Yeah. So when you identify these equivalence classes, what you are doing is that you are, generating something interesting, and those are called quotient spaces. Okay. So look at this figure. You have what? You have some set, and inside that set, you have some classes that are disjoint from each other, right? And if you consider these disjoint pieces and you make a new set of these disjoint pieces, some set of these equivalent classes, what you get is that a set of all classes, right? All the equivalent classes, and that is called a quotient space. So